Hi, my name is Luis, and I'm here to present my work, Design and Mechanical Properties and Acoustic Absorption of an Auxetic Structure with Thermoplastic Polyurethane. Different materials have emerged in recent years in response to the requirements of various engineering sectors, such as the automotive or space industries, to be used in shock absorption, acoustic insulation, or lighter structures. The extraordinary mechanical properties of auxetic materials can meet these needs and provide new scientific and technological advances. The word auxetic comes from the Greek auxetikos, which means that which tends to increase. When these structures are stretched along a horizontal axis, they tend to expand on the vertical axis. And when they are compressed on the vertical axis, they contract on the horizontal axis. The relationship between these deformations is explained by the Poisson ratio. The Poisson ratio nu of a material is the ratio between the lateral contractile deformation and the longitudinal tensile deformation of a material subjected to tension in the longitudinal direction. That is, it shows how much a material thinks when stretched. As the opposite occurs in auxetic materials, they have a negative Poisson coefficient. This coefficient originates from their geometry and the way they deform under unaxial loading, which can operate at any scale. Therefore, auxetic materials are classified by their geometry or deformation mechanism. Within the geometry, three basic structures are identified: reentrant, chiral, and rotational rigid. Modeling different materials according to this classification to obtain a negative Poisson ratio improves many properties such as greater resistance to plane strength fracture, greater shear modulus, indentation resistance, fracture toughness, or energy absorption. Particularly in sound, auxetic materials have attractive acoustic properties at low frequencies, and auxetic forms of polymeric and metallic foams have improved acoustic absorption compared to conventional materials. This work aims to design a chiral auxetic structure printed in thermoplastic polyurethane and measure its sound insulation capacity inside an impedance tube. The structure is a cube with a height, width, and depth of 64, 54, and 45 millimeters. The thickness of the entire structure is 1 millimeter. The geometric pattern is classified as chiral and consists of inclined squares with circles in their corners. On the side, it has a pattern of overlapping empty squares. Two designs were printed on an Ultimaker 3D printer with a TPU Stomer and another in TPU NinjaFlex. The first part of the study consisted of measuring the deformation of the material. It was placed between a universal tension machine and it was compressed to 15 millimeters. The results are shown in the following four graphs. The experiment was repeated several times to verify that very similar data were obtained, which ensured the determinate characteristics of the material. First, we have these two force strength curves, normalized to the average of the vertical and resultant distance. The curves decrease because the y-axis is compressed downwards and the x-axis is compressed inwards. The NinjaFlex structure have a Poisson ratio of minus 0.094 and the TPU structure has a Poisson ratio of minus 0.12. Then we have the stress strength graphs. For the NinjaFlex structures, 25 newtons were required, and for the TPU structure, 120 newtons were required to compress the 15 millimeters. In this interval, both show elastic behavior that reaches their yield point. The second part consisted of measuring the acoustic insulation of the materials. An impedance tube was designed with 4 zone intensity sensor purchased by Pasco, based on other similar works, and the ISO 5342 standard, which indicate the basic requirements in the material and dimension of length, the diameter of the tube, the size of the speaker, and the distance of the microphones at the sample to be studied. The tube was made of 160 millimeter diameter PVC tube, lined inside with foam to attenuate outside noise. According to the tube diameter, a range of study frequencies was determined from 20 to 1250 Hz. And with this, the position of the sensors were determined. Two sensors were placed between the sound source and the sample, one pointing towards the speaker and another to the sample. The other two sensors were placed behind the sample, one pointing to the sample and the other pointing at the end of the tube. They were classified as A, B, C, and D, with D being the sensor closest to the speaker. The end of the tube was anechoic, filled with foam to dissipate the generated waves. The four sensors and the sound source were connected to the Pasco Universal Interface. The speaker was programmed to send a sinusoidal wave with an initial phase of 1/2 P and an amplitude of 8 volts in frequency intervals of 125, 250, 400, 500, 800, 1000, and 1200 Hz over 0.27 seconds. The fast Fourier transformation function was used to collect data which decomposes the received sound into the corresponding frequency and shows the intensity captured in volts. The results are reported in the following intensity frequency graphs, indicating the data collected by each of the four sensors. The different curves shown refer to each change in compression: 0, 3, 6, 9, 12, and 15. There is a change in intensity detected by each sensor as the sample were compressed. However, a more in-depth analysis is still needed in that part, but at least a similar behavior has been observed, only by changing the frequency for each compression used. In addition, for future measurements, the response based on the orientation of the windows within the material and the buckling needs to be analyzed.